Today we are going to discuss electric potential and capacitance, right? Just like the electric force and the charge, electric potential is also another property of the field. Okay. And now today, first of all, we will start from electric potential. Today we will start from electric potential. Are you clear? Okay.
Yes,
Then we will discuss about the capacitance within 4 to 5 lectures, right? First of all, I am going to revise some basic equations from your previous classes. Please note it down. I hope all of you have already remembered that about the work done. All of you have know about the work done. What is the work done? Work done is, the first one is the work done by constant force. Note it down, please. Work done by constant force, which is W is equal to F into S, where F is your force, F is the force, and S is the displacement, right? When you expand this equation, you get also W is equal to F S cos theta. This is the, what is the theta here? Theta is the angle between F and S. Okay. These two are the equations of work done by the constant force. Similarly, the work done by variable force. What is the work done by variable force? In case of variable, if your force is variable, then the equation of work done is W is equal to F dot dr from displacement R1 to R2. This is your equation for variable force. Okay. Note it down, please. Note it down, please. All of you have noted it?
yes, sir.
Okay, good. And now, in the next heading, we are going to understand work done in external electric field. Work done in external electric field. Okay. Note it down, please. Work done in external electric field. In this, we are going to take an electric field. In this, we are going to take an electric field like this. Okay. This is your electric field. And we are considering here an electric charge which is placed at this point. This is your electric charge. Okay. Now, can anyone tell me what will be the direction of force acting upon this charge due to this field? This charge is positive in nature. You can take it. Can anyone tell me what will be the direction of force acting upon it? I think the force acting upon this charge is along the direction of field. Are you clear or not? Hello?
Yes, sir.
Yeah. This is the force acting upon this charged particle. So we can write here electric force on Q. What is the electric force on Q? This is your F of electric. This E represents electric. E is equal, Fe is equal to Q into E. This is your equation number 1. And now what will happen if we apply, this is your electric again. What happens if we apply an external force upon this charged particle in opposite direction of the F external? Then we can draw it like this. This is the force acting upon this charged particle in opposite to the direction of F of electric. Okay, you can write it F EXT. EXT in the sense F external, right? So we can write here external force to be applied on charge Q. To be applied on charge Q, F external. This can be written as F external is equal to the F of electric with negative sign. Why we are applying here negative sign? Because the direction of F external is just opposite to the direction of F electric. Are you understand, Nawal, Matthew?
Yes, sir.
All of you are understanding the reason behind this negative sign?
Yes, sir.
Yeah, it is because the electric force acting upon the charged particle is just opposite to the F external. Are you clear? So we can write here F external is equal to minus of F electric. This is your equation number 2. Now, what will happen if we put equation of 1 in equation 2? We can write here F external is equal to minus of Q into E. Okay. This is your F external of minus of Q into E. This is your equation number 3. This is the amount of force. Okay. This is the amount of force acting upon the charged particle externally, right? And now, what will be the amount of work done due to this external force? How can we calculate it? We have already know the equation of the work done is by variable force, W is equal to integration of F dot dr, right? From R1 to R2. So we can write here, what is the work done now? Work done by external force in carrying charge Q from A to B. Suppose that we are carrying this charge from point A to the point B. Okay. Then in what amount the work to be done? Okay. We can write here W external is equal to integration of from R1 to R2 F of external dot dr. This is your equation number 4. Now put value of 3, put put 3 in 4. We have in equation 3 F external. F external is minus of Q into E. So we can write here W external is equal to integration of R1 to R2 minus of Q into E dot dr, or we can write here W of external is equal to minus of integration R1 to R2 Q into E dr. This is your equation of work done in carrying this charge from position A to the position B. Are you understand all of you? Matthew and Nawal?
Yes, sir.
Yes, sir.
Any issue in this?
No, sir.
Okay, good. Note it down, please. This is the work done by external force. Remember that, okay? You can write it, just 1 second. I am write it clearly first. W external, right? This is the work done by external force. Note it down, please. Have you noted it?
Yes, sir.
Matthew, have you noted it?
Wait, sir.
Okay. Please note it down fast.
Done, sir.
Okay, good. Now, I'm going to remove it just 1 second. W external. I am going to write here again this equation. W external is equal to minus of integration R1 to R2, sorry, RA to RB. What is your R1, R2? Yeah. Just 1 second. This is your A and B. Okay, note it down here, RA and RB, because we have taken the position in terms of A and B. Okay, note it down here, RA, RB. Okay, RA, RB. Please make this correction. Okay, next one, RA, RB, Q into E dot dr. Right? Then, if you want to calculate the work done by electric field, then how can you calculate it? So please note it down. Work done by electric field. We have already know the relation between the electric force and the external force. We can write here W of electric force is equal to the W of external with negative sign. Okay, because both are in opposite. So we can also write W of electric field is equal to minus of what is your W of external? W of external is integration, 1 second, minus of what is your W of external? Minus of integration RA to RB Q into E dr. This negative and negative makes it positive. So work done by electric force is equal to integration of RA to RB Q into E dr. All right. Have you, are you understand or not? Hello?
Yes, sir.
Yeah, good. Next one. This is also the equation from, okay. Now, what will happen if your electric field is uniform? What will happen when your electric field is uniform? So you can write here, for uniform electric field, we can write W of external, this equation again, okay, I am going to write here, W external minus of RA to RB Q into E dr. Again we write here W external is equal to, you can take QE outside from the integral because Q and E are the constant. This is your RA to RB and dr is your differential part. Okay. After integrating this dr, you get R. So we can write here minus of QE in bracket R from RA to the RB. This is your W external. Again, W external is equal to minus of Q into E. What is your RA to RB? RA to RB can be written as RB minus RA. Okay? RB minus RA. So, what is your RB and RA? Remember that RA and RB, the position vectors, okay? RA and RB are position vector of and B, okay? Position vector of A and B. And we have already know in terms of displacement vector, we can write it RAB as RB minus RA. I hope you have already know from your vector chapter of class 11. So if you replace this value, I mean RB and RA from this value, then we can again write it just like W external is equal to minus of QE into RAB. This is your vector quantity. Electric field is also vector quantity. Okay. Note it down, please. And these vector and vector after multiplication through dot product makes it scalar. Okay. Note it down, please. Have you understand? Nawal, Matthew, all of you understanding this point?
Yes, sir.
Yes, sir.
Any issue? It is totally clear or not?
Yes, sir.
Okay. Note it down, please. Can we move on? Nawal,
Yes, sir.
can we move on? Matthew,
Yes,
Yes,
sir.
sir.
Yes, sir.
have you noted it? Okay. And now we have a question here. Please note it down. Find work done by external agent. External agent in the sense external force, okay? In slowly shifting a charge, Q is equal to 1 microcoulomb in electric field. In electric field. Note it down, please. Just 1 second. No, in electric field, and the electric field which is given here, E is equal to 10 to the power 3 I cap volt per meter from point P 1, 2 to the point Q to the point Q 3, 4. Okay, this is your question. And now we are going to solve it. What is the solution? There is two to three informations are given here. The value of charge is given here. Q is equal to 1 microcoulomb, and value of electric field is given as 10 to the power 3, right? And now what is your point P? Point P is given as 1, 2, and position Q is given as 3, 4. You can make it 1 as I cap, 2 as J cap, 3 as I cap, and 4 as the J cap. Are you understand, Nawal and Matthew?
Yes, sir.
Okay, right. So we can write here the equation of W external is work done by external field is minus of Q into E. We have this equation here. You can look at here. This is your equation also. Minus of Q into E, RB minus RA, but there is position vector is given in terms of P and Q. So we can write here W external is equal to minus of QE, RQ minus RP. Okay? RQ minus RP. Note, write it here. Minus of what is the value of Q? This is the 1 microcoulomb. You can write here 1 into 1 microcoulomb is generally 1 into 10 raised to the power minus of 6 coulomb. So you can place it here 1 into 10 raised to the power minus of 6 into what is the value of E? Value of E is given as 10 to the power 3 in the direction of I cap. Okay. Now what is your RQ? RQ can be written as 3I. From this point you can look here 3I minus 4J, 3I plus 4J, because both of the values are given in positive term. 3I plus 4J minus what is your RP? P can be written as I plus 2J. Okay, I plus 2J. Then What will be this value? This is your 10 raised to the power after calculation, 10 raised to the power minus 6 and 10 raised to the power 3. Can be written as 10 raised to the power minus 3 I cap. In bracket, you can write here 3I plus 4j minus I minus 2j. Write down here W external is equal to 10 raised to the power minus of 3I cap. 3I minus I is your 2I and 4j minus 2j is 2j. 2I plus 2j. Okay. Then we again write here 10 to the power minus 3 I cap. 10 to the power minus 3 I cap can also be written as 10 raised to the power minus 3 I cap plus 0j. Can we write it or not? Nawal and Matthew. Can we write this value
Yes,
just
sir.
like this or not? Hello, Nawal.
Yes,
No,
sir.
sir. We need to multiply it by 2.
Yeah. Nawal, are you understanding this point?
Yes, sir.
Okay, good. And 2I plus 2j. Now please multiply all of these values with their respective terms. 10 to the power minus 3 I cap and 2 I cap will be 2 into 10 raised to the power minus of 3. 0j and 2j will be 0. Finally, you get 2 into 10 raised to the power minus 3 joule. Okay. This is your final value of W external. All right. All of you are understanding this question?
Yes, sir.
Note it down, please. Have you noted it?
Yes, sir.
Matthew, have you noted it or not?
Yes.
Okay, good. Now, next question. Calculate work done by external agent by external agent in carrying two millicoulomb. MC in the sense millicoulomb, right? Charge from A 0, 0, this is your position vector, to the position B 2, 0 in electric field, and the electric field is E is equal to x plus 2y I cap plus 2x j cap Newton per coulomb. Note it down, please. Note it down, please, your question first, then we will solve it. Have you noted it?
Yes, sir.
Okay. Nawal, I am just asking to you that, can you tell me which one concept can be used here? Nawal, can you tell me please? Which one concept can be used here? Work done by variable force or work done by constant force?
Variable force.
Variable. Why? Because the values of electric fields are given in terms of variable. This is your x and y. Are you understand?
Yes, sir.
Okay, good. Now we are going to apply here. The given values are Q is equal to, what is your value of Q? Q is your 2 millicoulomb. You can write here 2 millicoulomb, which is 2 into 10 raised to the power minus 3 coulomb. Okay. Then we are going to apply our main equations W external from A to B. From A to B, W external is RA to the RB minus of QE dot dx or dr. Here your values are given in terms of x. Okay. So we can write here dx now. Are you understand? This is our main equations. Now we are going to put all of these values. RA. You can look at here. What is your point A? If you are choosing these 2 points, this is your point A and this is your point B. Point A is 0, 0. 0, 0 denotes the origin and B denotes 2, 0. This is your I and J both are 0. Hence, we can say that this charge is placed at the origin of the coordinate system. Am I right or not? Am I right or not? Nawal, can we say it or not?
Sir.
This charge particle is placed at the origin. If it is placed at the origin, then we can write here the value of RA is 0. And what is your RB? RB is your, this is your I, okay. In terms of X, this is your 0 and the another point is 2. So we can take it like 0 to the 2. Why? Because in the coordinate of y direction, you can look, it is at 0 and again at point B, y is 0. Are you clear or not? So we can say the body is, the charge is displaced from A to B only and only along X axis. Now, if you try to see this charge on the, in proper diagram, then you can write it here. This is your point B. This is your point B. This is the direction of I. Point B is 2, 0. Are you understand? Nawal,
Yes, sir.
are you understand? This is a proper diagram. Okay. And you can make it here. This is your J cap. Okay. This is your J cap. Then what is the value of Q? Q is given here 2 millicoulomb. 2 millicoulomb is 2 into 10 raised to the power minus 3 coulomb. And QE, what is the value of E? E is given as x plus 2y I cap plus 2x j cap into 2xj x 2xj, right here 2xj also I cap plus 2xj is written here dot, this is your dx, so we can take here dx in the direction of I, because in the direction of j all of the coordinates are 0, so we are taking here dx with I direction. Are you clear? Nawal, are you understand this
Yes,
point?
sir.
This point, are you clear or not? Why we are taking here
Yes,
I
sir.
cap only, not j? Why we are taking here dx I cap, not j cap? Can you tell me,
Because it's
please?
in the direction of I.
Yeah, because all of the values are given in I direction. In the in the j coordinate, all of the values are okay 0, right? So we are taking here I cap only. And now you can also write here x is equal to 0 and y is equal to 0. Both are 0, right? So again we can write here W external from A to B is equal to minus of value of x is 0, y is equal to 0. This is the 2 only. 2 into 10 to the power minus 3 is constant. We can take it same as it is. And after integrating x, we get x square by 2. 1 second, just 1 second, please. I cap x plus 2i. No. Yeah. Look at here. Multiply this value with dxi and 2xj. I mean, j cap is 0 here. You can take here 0j also. So we can write it x plus 2y dx plus 2xj plus 0j is equal to 0. Again, integration of x is 0, y is 0. This is your 2. You can take 2 into 10 raised to the power minus 3 outside. 2 into 10 raised to the power minus of 3 outside. Okay. After integrating x plus 2y, first we are going to integrate x. Just 1 second. I am writing again same value. Okay. In the next step, we will integrate it. X plus 2y dx. All of you are understanding till this point?
Yes, sir.
Any issue? Matthew, are you clear or not?
Yes, sir. Clear.
Note it down first, then we will solve it in okay from next step. Can we move on?
Yes, sir.
Yes, sir.
Okay, I'm going to remove this. Yeah, we have this equation. Again, I am writing here. W external A to B is equal to minus of 2 into 10 raised to the power minus 3. X is 0, Y is 0. 2 x plus 2y dx. Okay. From this equation, if we observe this, then you can understand that x have its differential part dx and y have no differential part. Are you clear or not? I mean, the function is okay. We can integrate those functions we have already differentiated. Are you understand or not? From your calculus, Nawal. Uh, Nawal, are you understanding or not?
Yes, sir.
Okay. We can integrate only and only those functions which are already differentiated. Okay. So from this equation, we can see that x is differentiated here. Okay. You can look at dx. Dx represents that x is differentiated here, but there is no any differential part of the y. So we are going to take y as constant, right? After taking it as a constant terms, we can write here minus of 2 into 10 raised to the power minus 3. After integrating x, we get x square by 2. This is the integration of x from 0 to 2. Okay. And 2y, because value of y is 0 here, so 2y will be 0. When you expand this value, you get 2 10 raised to the power minus 3. Put the value of 2 at the position of x first. We can write here 2 square over 2 minus, put 0 at the position of x. This is your 0 square over 2. Again, we get minus of 2, 10 raised to the power minus 3, 2 to the 4 over 2. This is your 0. Have you noted this part or not? Which I am, okay, removing here.
Yes, sir.
Okay, okay. And now, W external from A to B is minus of 2, 10 raised to the power minus 3. 4 over 2 is 2 only. 2. You get minus of 4 into 10 raised to the power minus 3. This is your external work done from A to B. Okay. This is your final answer. Note it down, please. Can we move on?
Yes, sir.
Yes.
Okay. Now, the next point is conservative electric field or conservative field, you can also say. To understand the conservative field, first of all, you are going to understand conservative force. Okay. And by the help of conservative force, we will understand conservative field. Are you clear? Conservative electric field. And potential. Note it down, please. Conservative electric field and potential. Okay. First of all, we will understand conservative force. What are the conservative force? Any one of you can tell me any example of conservative forces? Nawal, can you tell me? Matthew, can you tell me conservative force? Any example of conservative force?
Gravity,
Sorry?
gravitational force,
Yeah, exactly. You are right. Gravitational force. Okay. Spring force, electric force. All of these forces are the conservative forces, right? And what is the definition of conservative force? These are the forces which are independent on the path. Okay. These are the forces which are independent on the path. It only and only depends on initial and final positions. Okay. Write down here. Forces in which work done is independent of path and depends only on initial and final position. Initial and final position. Okay. Are known as conservative force. Are known as conservative force. Okay. Such as gravitational force, electric force, etc. If you want to understand about the electric force, then you can write here. We are taking here an electric field like this. This is a field. In this field, there are the 2 points in which a charge is carrying from point A to B. You can carry out this charge from this path. Either you are carrying the charge from this path Either you are carrying this charge from this path. Okay. It doesn't matter. This is your path 1. You can take it as path 2 and path 3. Okay. It doesn't matter what is the path of the charge from A to B. Okay. Your work done, work done from path 1 is W1 and work done from path 2 is W2, and we are taking work done from path 3 is W3. All of the work done will be same, which is further equal to the integration of minus of Q dot dr from point B to A. Sorry, this is B and A. Okay. Are you, sorry, B to A. Are you clear or not? Hello?
Yes, sir.
All of you are understanding or not? Matthew,
Yes, sir.
Matthew, it is clear?
Yes, sir.
Okay, good. And now, we are going to again understand in some another points here. Point 1. Remember that field corresponding to conservative forces are always conservative. Okay. Field corresponding to conservative forces are conservative. Okay. I means if the force is conservative, if there is a field which is generated from a conservative force, then remember that it always be conservative. Okay. Conservative. Like electric field and gravitational field. Second point. Second point. Total work done by conservative field in a closed path is 0. Try to understand here. Suppose that we are going to take again a field. This is a field. This is a field here. And we have a charge which is moving in a closed path. Okay, suppose that this is your point A, and this is your point B. In first part, this charge is carried out from, this charge is moving from B to A. Okay, this charge is moving from B to A. So we can take it as W1. And when this charge again moving from A to B, then we can take it work done as W2. And we have already know W1 and W2 are equal. Am I right or not? Am I right or not? W1 and W2 are equal. Is it is true or not?
Yes, sir.
So we can write W1 minus W2 is 0. Okay. Hence, in terms of electrostats, we can write it W is equal to integration of minus QE dot dr. Okay, minus QE dot dr for a closed path. This closed path can be represented in this equation like this. We can make here a circle on the integral sign. Are you clear or not? This circle on integral sign represents that integration are carried out with respect to a closed path. Are you understand or not?
Yes, sir.
Okay. Integration of sorry, integration with respect to a closed path minus QV dot dr will be 0. Okay. Why? Because work done is 0. Note it down, please. Nawal, is there any issue in this equation, in understanding this equation? Are you clearly understand or not?
Yes, sir.
Okay, good. And Matthew?
Yeah, understand.
Okay, good, good. If there is any type of issue, okay, you can feel free to ask me. In the next point, have you noted it?
Yes, sir.
Okay, good. In the next point, if we are going to integrate with respect to a line, then what will happen? Once again, write down here line integral of electric field for a closed path is 0. I mean minus of Q integration of E dot dr is equal to 0. Or we can write here integration of E dot dr is equal to 0. This equation represents line integral of electric field. In the next point, if line integral of a field is 0, then that field can be represented as gradient of a scalar function known as potential. I mean integration of E dot dr is 0. Then we can write here E is equal to minus of d dr of V. This is your scalar electric potential. Okay, note it down, please. We will use all of these equations, okay, in further part. Have you noted it?
Yes, sir.
Yes.
Okay. Next point, electric potential difference. What is the electric potential difference? Electric potential difference. Okay. What is the electric potential difference? Any one of you?
The potential difference in electric
Yeah.
field.
Remember that electric potential is just another way, okay, to define the electrical properties of the charge in scalar form. Are you clear or not?
Yes, sir.
We have already studied in the previous lecture Gauss law. All of you remember or not? All of
Yes.
you remember or not about the Gauss law?
Yes, sir.
What was, okay, can you tell me uh, what is the significance of the Gauss law? What is the significance of Gauss law? Gauss law is just a method, a shortcut method, which provides to calculate the electric field without the calculation of electric force between the charges. Am I right or not? Hello?
Yes, sir.
Are you understand or not? What is the role of the Gauss law? Gauss law is just a shortcut method to calculate the electric field. Okay? Without the help of the Coulomb's law, we can say. All right or not? Just similarly, electric potential is another quantity, okay, which defines electrical properties of the charge in scalar format. Okay? Are you clear?
Yes.
Sir.
Good. So please note it down. Note it down, please. Electric potential defines electrical properties of a charge in scalar form. Okay? In the second point, you can write electric potential is always a property of single charge only. Note it down, please. Note it down, please. Then we will go to calculate it. Okay? Have you noted it?
Yes.
Yes, sir.
Now, we are going to take a charge here. This is your positive charge. Okay. We have taken here a positive charge Q. Then, can you tell me, is there any field is created by this charge or not? Yes. If there is a charge, then it associates a field also, okay, in their surrounding. We are taking two different points in the field of this charge, and these points are point A and point B. Okay. These points are point A and point B. Right? We are going, sorry, we can assign here the potential at point A is VA and potential at point B is VB. Right? Are you understand or not?
Yes, sir.
Okay, we are considering here potential at A is VA and potential at B is VB. Then when we are going to transfer, or you can say we are carrying a charge from B to A, then can you tell me, is there any work done is possible or not? Okay. Is there any work done is done or not? Work is done or not? Yes. Why? Because point A is very close to the positive charge capital Q and B is slightly away from the positive charge capital Q. So the effect of this positive charge at point A is great, is more than the point at B. Are you clear? Hence, we can say when we move a charge from B to A, okay, work should be done here. Okay. And now, what will be the potential difference here? The potential difference can be written as VA minus VB. I mean the difference of potential between these 2 points A and B are known as electric potential difference. Okay. So please note it down. Potential at A with respect to B here. Right. This charge can be also known as the source charge. This charge can be also known as the source charge. Now, what will be the change in potential here? This change in potential is represented by delta V is equal to VA, I mean potential at A minus potential at B is equal to W of B to A externally, okay? Because potential at B is greater. Sorry, potential at A is greater than potential at B. So we are taking here delta V is equal to VA minus VB, okay? And this charge is carried out from point A to point B by external effort. So we can write here W of BA external, right? W of BA external over Q. This is your first equation of electric potential difference here. If your charge is 1 coulomb, then your VA minus VB can be written as W of BA external. Okay. This is the relation between electric potential difference and work done, right? In variable form, we can write here W of BA. We have already know the equation of W of BA external can be written as minus of integration RB minus RB to RA QE dot dr. This is your equation number 2. Now put equation 2 in equation 1, we get delta V is equal to VA minus VB is equal to minus of Q integration of E dot dr RB to the RA over Q. Q is cancelled with Q. You get delta V is equal to VA minus VB is equal to minus integration of RB to the R. 1 second, there is no more space here. First of all, note it down, please, till here. Then we will do it in the next part. Please note it down. Only one step is remaining. Okay. All of you are understanding, Nawal and Matthew. Is there any issue in
Yes,
all
sir.
of these equations? Nawal, is there any issue?
No, sir.
Okay, Matthew, clear or not?
Yeah, clear, sir.
Okay, note it down, please. Have you noted it?
Yes, sir.
Okay.
Yes, sir.
Yeah. All right. We can write it like this. Delta V is equal to VA minus VB is equal to integration of RB to the RA minus of E dot dr. Note it down, please. Can we move on?
Yes.
Okay. Now, if you want to define the electric potential difference, then we can write here is this is your definition of potential difference, right? Please write it down. Potential difference between two points is the work done by external force in carrying a test charge of 1 coulomb from one point to another against the electric field without acceleration. This is the definition. Please note it down. Note it down, please. Have you noted it?
Yes, sir.
Yes.
Okay. So today we are going to over this class right now. And just 1 second. There is 2 more equations. First of all, note it down again. This equation delta V is equal to VA minus VB is equal to minus of RB RA E dot dr. Okay. Note it down, please. This equation, or sometime it can be also written as. Note it down. Okay, I am going to remove it. Have you noted it or not?
Yes, sir.
Okay. We can write here delta V is equal to VA minus VB is equal to minus of E. You can take outside RB to RA, RB to RA, dr. This is your equation in. This is your equation for non-uniform field only. Okay. For non-uniform field. Okay. In constant terms, you can also write VA minus VB is equal to minus of E. You can take here RA minus RB also. Okay. This is your equation in terms of position vector, in terms of position vector, and you can also write it delta V is equal to VA minus VB minus of E RBA. Okay, this is your equation in terms of displacement vector. In terms of displacement vector. Okay, note it down, please. And this is used for uniform electric field. Okay, this is used for uniform field, right? Uniform field. Have you noted it?
Yes, sir.
Okay. Nawal and Matthew, is today's topic is clear or not?
Clear, sir.
Yes, sir.
Any issue in this topic today?
No, sir.
Everything is clear?
Yes.
Okay, sir.
Okay. All right. Then we are going to over this topic today, and we will continue from the next class.